So this is somewhat impromptu. I was asked to several people had expressed interest. I don't know why. Oh, mine's too old? Asked about geoneutrinos. The word has been mentioned enough times, so I decided I'd give one of my talks. And I just quickly assembled some. Well, I deleted slides from a talk I gave in New Mexico earlier this year. I start with this slide because I'd like to at least announce that anything I'm doing in this field, first and foremost, I'm extremely grateful to be able to work with quite a range of particle physicists who, for almost a decade now, have been bringing me along and educating me. So some of this talk involves my former PhD student, Yu Huang, who is, as far as I know, the first student in Earth Sciences to get a PhD in geoneutrino studies. Andrei Shramik was a postdoc working with me on this topic, and we'll see results from both of their work. Roberta Rudnick is an expert in the composition of the continental crust. That's the Maryland team. Steve Dye, a particle physicist at Hawaii Pacific University and also the physics department at the University of Hawaii. And John Learned, a physicist at the University of Hawaii, have been my long-standing collaborators. I met them in 2005, and we've been working together and publishing together for a long time. Myself, Steve, and Siji put together a proposal that was funded to look at the global picture of neutrinos. And Fabio Mantovani, University of Ferrara, Italy, physics, has been working closely with Yu Huang, myself, on a number of different topics, some we'll cover here. So it's really been a fun ride. No, I think we ended up with one. Thank you, June. And a lot of this is going to look at the question of heat production in the Earth. So just a few background slides. Geoneutrinos actually come from they're a byproduct of beta decay. And so the question you can ask is, does heat from radioactive decay drive the Earth's engine? So we're looking at plate tectonics, mantle convection, and the power to drive the geodynamo. So the fundamental driving forces in the Earth system. Cutting out a lot of background, so it's just a half-hour talk. We have a couple of different models that compete for the radioactive elements in the Earth. That is, uranium, thorium, and potassium provide over 99% of the radioactive heat production inside the Earth. The thorium-uranium ratio in chondrites is 4. Some people will say 3.9 plus or minus about 0.4. That would sum up all of the values. So that number is 4. Everybody's model fixes it to 4. The potassium-uranium is approximately 10,000. Okay, some people have finessed it and asked whether or not it's a little less than 10,000. The majority, that doesn't mean it's right. It's pretty comfortable with a number like 1.2 to 1.4 times 10 to the 4. So the potassium-uranium ratio being around 10 to the 4, the thorium-uranium ratio of 4 ends up giving you a reference frame that you can say uranium in the Earth describes the heat production in the Earth. Okay? So some estimates, I've eliminated all of the estimates, and I'll just summarize it up. One estimate would be 13 nanograms per gram in the total Earth, the metallic sphere or the core having a negligible quantity of uranium, thorium, and potassium, but that's a debatable issue. The silicate sphere, so in one reference state, we can think of the silicate Earth having 20 nanograms per gram uranium. However, the lower values get down as low as O'Neill and Palme 2008 model with 10 nanograms per gram. And Turcotte and Schubert, there's a few others, up around 30 nanograms per gram. So you can see there's a factor of 3 in the estimate of the uranium power in the Earth. Therefore, the same for thorium and potassium. All of these 3 models, plus all the other models, do assume thorium-uranium of 4 and Ku of 10 to the 4. This 20 nanograms per gram in the silicate sphere can be thought of as about half in the continental crust and half still left in the mantle. So that question of differentiation of the Earth has really already, at an amazing, fairly efficient level, taken a large amount of these elements out of the Earth's interior and stuck them up on the continental crust, a very thin veneer at the surface of the Earth. what is typical of when I've given this talk in physics departments, they often find this counterintuitive because uranium, the heaviest element, should be gravitationally stuck down at the bottom of the Earth. In fact, they're very frequently asking, why isn't uranium in the Earth's core? But they forget that gravity is a very weak force when compared to the electromagnetic force. If we look at the total heat radiated by the Earth's surface heat flow is 46 plus or minus 3 terawatts. And what you can see from the red pie and the blue pie here, this is in the reference model. Total radiogenic power is 20 plus or minus 4. I used my model for some reason. But you can rescale this to 10 terawatts of power or 30 terawatts of power. Now, let me highlight. It's just wonderful. 10 ppm equals 10 terawatts. ppb or nanograms per gram equal 20 nanograms per gram is 20 terawatts. So the uranium content and terawatt output scale exactly. It's a wonderful little fun fact. The continental crust. This is one of these models, observations that a vast amount of the geological community agrees upon, that the continental crust has 7 plus or minus 1 terawatts. Rudnick and Gao is one of the favored models in the treatise of geochemistry, the composition of the continental crust. But I can tell you what Yu Huang, Roberta, myself, Fabio, and Slava all together put in a major effort. I'll just highlight it a little bit briefly a little later in the talk. Also interrogated this, and in fact, we come up with the number of 6.8 plus 1.4 minus 1.3. So to the best of our knowledge, it's 7 plus or minus 1 terawatts. If you have a total 20 terawatt radiogenic production and 7 there, that only leaves 13 left in the mantle. So that's that scaling relationship. You're just forced into that. If you have 7 in the crust and a model of 20, that becomes 3 terawatts. So this is also something that you can keep in mind. So if you have 20, it's about 40% of the total. The remaining amount of heat in the Earth system can be considered primordial heat, the heat associated with the assembly of the Earth. The Earth is 6 times 10 to the 24 kilograms. Something coming in is 20 kilometers a second. That gives you 10 to the 30 plus joules. And how fast we dissipated that is really a very, very large unknown. In addition to that budget of heat that was primordial, we have the differentiation of the Earth's metal into the gravitational center. That gravitational energy has evolved through time as a heat dissipation from the core to the ceramic oxide surrounding it. Our best estimate for heat flux out of the core, this is a little bit old, but I think this would be consistent with Lay, Buffett, and Hernlin. They had estimates as between 4 and 15. Last week we heard a lot of people liking estimates between the 10 to 15 terawatt coming out of the Earth's core. I've put a tilde 9 as some sort of approximate number coming out. I'm not fussed about that. You want to change it to 13, which I've heard some people say. Fine. I don't think it's that tightly constrained right now. However, if we take these 3 numbers, add them up, subtract it from 46, we're left with 18. This is the kind of knowledge base that we have, what would be the amount of primordial energy left over in the Earth system. Okay? All right, let's get directly into neutrinos themselves. And to really talk about neutrinos, we need to talk about the fundamental states of matter here. The most important is the first generation of matter states, the up and down quark, which are the fundamental particles that are used to build protons and neutrons. These are complemented by electrons, the charged lepton, the electron surrounding the nuclear materials here, representing the first state of matter. And then down at the bottom here, we have the neutrinos. So neutrinos, in the terms of the family of materials, they are leptons, and they are uncharged lepton. That's charged, that's not charged, and that actually adds to its attribute. These uncharged particles actually are manifested through the weak force, and the W plus boson and the W minus boson are the moderators for their interaction. So during beta decay, you'll see these produced. In addition to all of these particles, we have the antiparticles. We have the anti-up, anti-down, the positron, which is familiar to most people, and the anti-electron neutrino. The anti-electron neutrino is the one that's actually produced inside the Earth during beta decay. Many people have talked about neutrinos, say, I know neutrinos, and they're really thinking about the neutrinos that are formed in the Earth, the sun's core during proton-proton fusion. It's the most robust environment for the production of electron neutrinos. The shower from the sun is about 10,000 of electron neutrinos, about 10,000 times greater than the flux from beneath us of electron antineutrinos from the Earth. The electron antineutrino flux from the Earth, your little fingernail is approximately a centimeter square, and our flux is about 6 million per second centimeter square. Okay, so everywhere in this room there are electron antineutrinos passing through all of us and not interacting. If you're about my age, you've had a probability of one antineutrino interacting with my body during my lifetime so far. So they really, although we're fluxed constantly, they just do not interact with matter. So there's the typical flux that is occurring inside the Earth. To put this in perspective, the production of electron antineutrinos, we have a neutron. A neutron is made up of one up quark and two down quarks, and these are bound by gluons themselves. The beta decay process, which is very common, uranium, thorium both have alpha and beta decay, so it's the beta decay steps in the uranium-thorium scheme. Potassium produces both an antineutrino and a neutrino because it's a branch decay system. Rhenium, lutetium, rubidium, carbon-14 also goes through beta decay. So during the transformation of a neutron into a proton, you have the down quark transforming into an up quark, which is moderated here by this W boson. And during this transition, you have the production of an electron anti, with the bar on top, electron antineutrino. So that's specifically the flux that's coming out of the Earth that we're trying to measure. Yes?
What about samarium that is important, I think, in terms of...
The samarium decay schemes, both 146 and 147 are alphas.
So you cannot see...
We cannot see the alpha.
That's important for the heat production, because that's...
No, the one, I can't do the 146 right off because I just don't know the energy of that decay, but the 147 is really nothing.
Yeah, not 147 is nothing.
Nothing, absolutely nothing. The fourth element system to really have any influence is rubidium-87, and that's about 0.8% of the thermal budget of the Earth. The thermal budget from radioactive decay, relative to uranium, thorium, potassium. All right. How do we detect electron antineutrinos, and why did it? Oh, well, let me just take a brief moment. So, as it turns out that in the turn of the last century, we basically had a lot of discovery of electrons, the nucleus, the neutrons, protons, as well as radioactive decay. And as it started out, we had alpha, beta, and gamma decay modes. And the alpha and the gamma decay modes were pretty understandable, but for a while, physicists were gnashing their teeth over the beta decay mode. And part of that was all associated with really trying to understand the conservation of energy in that system. During the alpha decay mode, the product and the reactant was going in opposite directions, making a little bit of sense. But in the decay mode of the beta decay, it seemed that there should be three bodies, but no matter what they did, they couldn't invoke a third body. It took at least a not-so-brave Wolfgang Pauli in 1930 to suggest that there must be a third particle that's involved in beta decay. And in fact, he was so brave that he didn't go to the meeting, didn't go to the conference. He actually sent his graduate student in a handwritten letter to the conference. And this is the total publication associated with this concept. Wolfgang Pauli had them announce that it's regrettable, but the only way to solve the beta decay problem was to invoke a particle that will never be detected. He also went on to say that if it ever was detected, he would buy the detector a case of champagne. I'll get to that in a minute. How was it detected? How is the electron antineutrino detection process occurs? Here is a diagram which is showing electron antineutrino energy versus a flux, if you will, proportional flux. So it is detected through what's called inverse beta decay, where an electron antineutrino plus a proton, and that's a free proton. So we have liquid scintillation detectors Just think of it as a detector about the size of this room, completely filled with liquid scintillator. Liquid scintillator. When it was first described in the New York Times, it was referred to as a mixture of baby oil and benzene. Okay? When I talk about a proton, I'm talking about a free hydrogen atom that is a hydrogen atom in this hydrocarbon chain. Okay? So the interaction is electron antineutrino hits a free proton in this environment, transforms that proton into a neutron plus a positron. Positron doesn't exist for a long period of time, so that is in matter. It's an antimatter, so it will react instantly, and the neutron will actually find a home with another proton shortly thereafter. However, to activate this channel, if you will, this electron antineutrino has to carry 1.8 million electron volts of energy to actually accomplish this reaction. So what you can see here is that only the green and the red beta decay steps are higher enough energy to accomplish this reaction. This is specifically 234 protactinium and 214 bismuth. You'll see this has 2.3 maximum of 2.3 endpoint energy, 3.3 endpoint energy. The thorium decay chain is actually weaker. The actinium 228, 2 MeV, and bismuth 212, 2.3 MeV. What you can see here is the proportional contribution. This adds up close to 100%. Is really scaled as a function of the maximum energy. So this is the brightest of the electron antineutrino signals that we can see. And they're represented right here on these two chains. And as you can see, this has got already a beta step. This has got 2 beta steps and 3 beta steps. So we don't even see all of the beta steps from this decay chain. What's really regrettable in this system, I'll just highlight that potassium 40 goes through a beta decay step to calcium 40, but we cannot detect the potassium 40. We'd need to access it by another channel that only needs 1.3 MeV, and that channel right now appears to be, it's rather challenging, but about 10 kilotons of helium, liquid helium-3 for a year could get us a potassium number. It's impossible.
How does the geoneutrino goes from the deep Earth to the surface, and do all geoneutrinos able to get to the surface? Does it get mixed in the mantle or something?
Okay. Question was really how do geoneutrinos pass out of the Earth? So that brings out, I forgot to mention this fun fact. It doesn't matter if it's an electron antineutrino or any form of neutrino, any form of antineutrino. The antineutrino and neutrino have a probability of passing through a light year's distance of lead at about a 50% chance. The other time, it will make it all the way through and never interact. So the Earth, or all matter, is essentially transparent to neutrinos. They just pass through the Earth. They pass through matter for the most part. They have an exceptionally small interaction cross-section, which is around 10 to the minus 45 centimeters square. They're not charged, and so that really, and they're about 1 million times less in mass than an electron. So they really are small and lightweight.
So what are signals from this detector the interaction of this light?
I'll show you in 2 slides. Okay, so this is the detector. I'll show you the energy plus right now I'll give you the background. So this is the experiment that occurred in 1956, and yes, these guys did get a case of champagne from Wolfgang Pauli. Fred Reines and Clive Cowan. Reines ended up getting the Nobel Prize for this experiment, in which this is their detector. Again, this is scaled down. This is a much smaller liquid scintillation device. Again, on the inside of the walls there were photomultiplier tubes looking at the scintillation volume, waiting for light to appear. They needed a bright antineutrino source. 10 meters away, right behind that wall, is the core of a nuclear reactor. Nuclear reactors undergoing fission will produce low and high mass fissionogenic products that are extremely rich in neutrons, and they want to march towards the valley of stability, so they're going to go through rapid beta decay, giving off electron antineutrinos, and they're of higher energy. So what was happening was electron antineutrinos were being seen by this scintillation volume. Here's the scintillation oil hitting a proton, immediately creating a positron and a neutron. The positron existing for on the order of 100 picoseconds because it just won't exist in this state of matter. And then we'd have these double gamma annihilations. So that's that 512 keV of energy associated with the massive electron. You'd have electron-positron annihilation. About 200 microseconds after this initial event, the neutron has gone through a thermalizing process, which is going to be cooling down, colliding with material in there, and ultimately finding a free hydrogen atom and creating deuterium. Neutron-proton fusing gives you deuterium, and that will give you an exact flash of light of 2.2 MeV of light.
I don't mean to be pedantic, but what's the temperature of a neutron?
Oh, not at all pedantic. It can vary. It depends. In a lot of nuclear reactors, we have what are called thermal neutrons. They're excited energy state, and so they're coming down from fast neutron to thermal, slow neutron to thermal neutron. A thermal neutron would be about 25 million electron volts, and so that would be that kind of number. But you can have, lots of these reactions will have neutrons with several MeV of energy, and that's an excited, really thermally hot neutron. Okay. Other questions like that, they're very useful. So in this kind of detection event, we're really talking about two flashes of light close in time and space. Remember, this flash, a couple hundred picoseconds. This flash, 200 microseconds. Second flash of known energy, 2.2 MeV of light. Let's look back in our record. About 200 microseconds before that, what was the flash of light? That was an antineutrino. That was its energy. Now we actually know which antineutrino it was. So two flashes close in space. This is actually 200 microseconds is going to make that neutron move on the order of a meter. So these two flashes must be a meter apart.
I think you just answered my question, but obviously the sun's producing a ginormous amount of.
Ginormal.
So, but you could line of sight. You could just be like, well, if the neutrino comes in this way, if you see two flashes, you could say something about it.
Love to do that. Love to do that. I'll hit on the question of directionality later, but due to the chirality nature of neutrinos and antineutrinos, or the helicity, the neutrino is left-handed, the antineutrino is right-handed. The antineutrino can activate this reaction. The neutrino cannot activate this reaction.
So the difference between the solar neutrinos and the geoneutrinos are just the energy, or there's something more fundamental?
It's the spin state of the particle. The spin state of the particle. So it just can't access this channel, cannot activate this reaction, even though there's 10,000 more per second. All right, covered this one. All right, so this would be an energy spectrum. I think combined the two slides here is giving you a sense. Really all you have to think about is this is the neutrino energy on the x-axis. This is some event rate for a kiloton year of detector, if you will. This is idealized. And by the way, there is a website, and it's mildly associated with the KITP because 2 weeks ago we had a meeting here on geoneutrinos. This is actually in a paper that I had in Physics Today that gives you the simple background. So I generated this ideal spectrum assuming a thorium-uranium ratio of 4, and I also asserted that the closest nuclear reactor was 1,000 kilometers away. So this would be a typical reactor spectrum. This is highly understood system. The uncertainties on this right now is around 3%, but we're trying to get them down to uncertainties on that spectral analysis to be 1%. If we can get that, then we have a better fidelity from our geoneutrino signal. What you can see is the thorium signal sits under half of the uranium signal, and the other half of the uranium signal sits at a higher discretely at a higher energy. If we get large numbers, about 1,000 events, we might be able to deconvolve the thorium-uranium ratio. But for the most part right now, we are asserting the thorium-uranium ratio is 4. So the question is, what can physics do for Earth sciences, right? So CAMLAN is, I'll give you a bit more about these detectors in a second, but CAMLAN is the Japanese experiment. Borexino is the Italian experiment. CAMLAN first came out with the result in 2005. They came out with an event in 2011, a publication in 11, and then in 13. We've had, I don't have a mention of it here, but if you were to go onto Google, type in Geoneutrinos, a Wikipedia page comes up. At least it does on mine, because I've visited my page a million times. But Andrei Sharamik and I did build a Wikipedia page on Geoneutrinos. On that page, we also announced all of the meetings that we've had to date. We've had 6 of these meetings in which the particle physics and the geology community get together and talk about these results. I was just talking to Claude Jopin and Thierry Lassière, who's a particle physicist, and the next meeting will be in June of next year, probably the first week of June in Paris. Why? But nonetheless, here are the results that have come out. So these are expressed on the y-axis as TNU, geoneutrino events seen by a kiloton detector in a year. We scale these all to this kind of event because the different detectors are different sizes, and even if you're a kiloton, you're not 100% efficiency, we correct for that efficiency. All right, so here, that's just the raw data, and now you're going to see the geology data. Michael?
Do you want to comment on the trend?
No. In fact, I've made a lot of comment about it, but when you see it like this, particle physicist says, it's all within 1 sigma. I have tried to make comments that, that's constantly decreasing. All within 1 sigma. It's a shutdown argument, they say every time.
If you view almost any of the particle physics parameters for the standard model, you'll see that they all converge very nicely for a while to a certain value, and then jump as the next generation detectors come online, and then converge to another value, and then jump to another value and converge nicely. It's a problem with estimating error.
And the other thing to keep in mind, I love the quote from John Bacall that's frequently pulled out. Half of all 3 sigma estimates are wrong. Well, who knows? So I wanted to give you where we're at. I wanted to leave in your mind 2 ideas. One is these uncertainties are getting much, much better. It turns out that, in 2005, they had 25 events, plus 17, minus 18. So they had very low statistics. I'll give you more of the data later. All right, we have crust near field, crust far field, and then 3 colors of green. The 3 colors of green would say silicate Earth models of 10, 20, and 30 terawatts. First takeaway message, no model is eliminated. All models are still viable. Doesn't matter if it's a 10, 20, or 30 terawatt Earth. Far field, near field, far field, near field. You'll see there's a difference. This is in Italy, that's in Japan. What you do in the near field is you say, I'm a detector. I'm going to look 500 kilometers this way, this way, this way, that way, that way. I'm going to do the geology as best as possible. I'm going to assert that the abundance and distribution of uranium is X, and that will give me approximately half of my signal. Far field crust, rest of the crust on the whole planet. So you can have as we stand here, you can have a geoneutrino event in Europe, and it could be seen by a detector in Santa Barbara, but it has a low probability of that detection. These detectors are sensitive, 1 over r squared, so the further it gets away, the less likely you're going to see it. So these terms, cosmic, chemical, geochemical, geodynamic models, really sort of speak to that issue. Yes, go ahead, Paul.
Close to Italy than there is to Japan?
Pardon me?
There's more crust close to Italy?
More continental crust, yeah. Yeah, the Borexino is at Gran Sasso, and Gran Sasso is in the Apennines, really close to Rome. It's between Rome and Pescara in the Apennines. Yes?
The cosmic chemical model, are you referring to Jawad's model or a Boyer and Carlson type model?
I won't say Boyer and Carlson model, but it could be O'Neill and Palme's model, or it could be Javois model. I just want to say it's a family of models, and I was searching for terms. Some people complain. In fact, I remember it was Louise who gave me a good suggestion. I think it was. She says, I used to call this the geophysical model, and I think you were the one who said geodynamic model. And I write in my papers, not all geodynamicists assert that it's 30 terawatts. But I can tell you, 2 weeks ago, Dave Stegman was here, and because of the core conductivity, he was highlighting that there may be 35 terawatts of radioactive power in the Earth's interior. Louise is saying, yeah. Keep it in mind. Do not eliminate it. I don't know what's going to happen if I go up to 35. Ooh, you know. But we have to see. We have to see. Go ahead.
Yeah, you're trying to understand these detectors here. How?
The next slide is actually on the detectors.
Okay, well, you mentioned something about making the corrections for the crust. Like, how much of the mantle do each of those detectors see? Is it basically like a cone? Or is it?
Yeah, you can think of it as the, well, let me turn it to you this way. The sun has some amount of uranium. It's 1 million times more massive than the Earth. And so you can just scale it up. It just has, that much more uranium, right? But it's 150 million kilometers from the Earth. And the probability of us detecting an electron antineutrino from the sun is 10 to the minus 5.
I guess what I'm asking.
So it is sensitive to that.
What I'm asking is, like, each of these detectors, are they seeing like the whole mantle, or do they?
Oh no, they see the whole Earth. They see the whole Earth. They see the Earth that is actually on the antipode, so that a electron antineutrino has a probability of passing straight through the core and hitting the detector. It has that probability.
What do you mean by geoneutrino event?
Well, a geoneutrino, okay, so electron antineutrinos are definitely emitted from nuclear reactors. So we refer to those as the reactor neutrinos, and we refer to geoneutrinos as only neutrinos produced during natural radioactive decay in the Earth. Right? Okay.
Reactor neutrino flux. You know what kind of reactor, how far.
And all of that is, yeah. So Paul's question was reactor neutrinos. We know them that well. This is a number that we do know very well. Every reactor, even the Bashir reactor in Iran is reporting its burning cycle. It's burn on, burn off. There are ways to actually measure it. There's a lot of people saying, what do they call it? The IAEA is showing up at the Bashir nuclear reactor on the coast of Iran. That's not the big worry. The big worry is what's happening in the centrifuge factories that they have. That's the really big worry, and we don't detect those. We cannot detect those because you have to be burning fuel for us to detect it with electron antineutrinos. It can't even be a stockpile. Go ahead.
It looks as if your crust is estimated really well. There are no error bars on the crust. How well do we know
Again, I'll just ever so briefly, in a couple of slides, actually get to some of that. There was a publication we put out. Remember that the Earth's crust is estimated at 7 plus or minus 1 terawatts. I have been asked by some physicists, could you put some error bars on the Earth's crust and mantle? Yeah, I just don't know how to make it so it doesn't look ugly on this diagram. I just really can't. So, I think one of the things the particle physics community has asked of us, and I've really put a lot of effort, is to characterize the uncertainties in our Earth system. Was there another question? All right, so let's just briefly, I'll talk about the family of detectors right on this slide and the family of future detectors on the next slide. So this is the Camland detector. It's in Japan. It's 1 kiloton. For scale, there's a human illustrated right at the top there. This is 13 meters across. This is 20 meters tall. The interior, the sort of bluish volume, is filled with this benzene and baby oil. The bottom down here would be a muon Vito layer of pure water. There's a parafilm layer on the outside where the photomultiplier tubes is. The black dots there would be photomultiplier tubes, so there's about 3,000 photomultiplier tubes there. Just for small experiments, these photomultiplier tubes run you around $6,000. There's 3,000 of them in there. And this actually needs a lot more photomultiplier tubes. This is a little over the 1.3 kilometers underground in formerly lead zinc mine, I think it was, in the Alps of Japan, roughly on the other side of the island from Tokyo, in the mountains there. This is the Borex. I'm going to get to that. That's really, yes. The Tohoku earthquake was a geoneutrino blessing. But fashionable Italians will wear white pants and green jumpers. So you can see legs of a person right there. This would be an image of the Borexino detector. It's substantially smaller, 0.3 kilotons, so it's really small. So from the Camland detector from March 2nd to November 12th, measured approximately 120 events. So you can see that that's approximately 12 events per year. That's it, one event per month. You can see that this was up and counting for a little less than 5 years, maybe 4 years, 14 events, so 14.3. Somebody goes, how can you actually calculate and measure 0.3 of an event? These probabilities, that is that you have so many events that are from the reactor, so many events from the geological environment, and that's how you actually partition the information. But you can see that the Borexino detector is getting about 4 counts a year, or 1 count every 3 months, or maybe 2 months, or something like that. And on a good year, you might get 5 counts. It's not a very fast count rate. And so you can see now, when you think about it, that double flash time and space, second one of 2.2 MeV, is fundamentally important for eliminating background because they see a lot of other kinds of events in these. And that's called muons, passing through the detector, penetrating deep inside the Earth. The Snow Plus detector, we hope it comes online. They've been having some technical problems. This was a very famous one associated with the Sudbury Neutrino Observatory, measuring neutrinos from the sun. This is actually the old Kamiokande detector redeployed. And now, of course, you may have heard of Super Kamiokande. The Super Kamiokande actually found out that neutrinos oscillate between 3 different eigenmass states. It got the Nobel Prize associated with that finding. And these are the present detectors. This is really expected to, this slide was made a year ago, and it's promised to come online in 2014. They're really stuck on this right now.
You get why the Italian detectors the same idea?
It's right, not adjusted. No. Okay. So this was my first publication with 75 of my closest particle physics friends. For the students in the room, I used to have a very hard and steadfast rule. I'll only publish papers where I know what's going on. 3 of those published pages, I know what's going on. I think I know a little something about proton decay. But the remainder of those 40 pages, opaque to me. But nonetheless, it was really a great experience working with the particle physicists. This linear experiment was a proposal. I guess it's not going to come up. I used to have it says canceled. And in fact, it looks like this is dead in the water. This experiment, about a year ago, the European Union looked at what their agenda was for the next 10 years, and they looked to cancel this. So this would have been really nifty at 50 kilotons. This would have gotten over 1,000 counts per year of antineutrinos from inside the Earth. 1,000 counts per year. Juno is going. Juno is a 20 kiloton detector, Jinping Underground Neutrino Observatory. It will be stationed approximately central between 2 very powerful nuclear reactors. They're hoping, the Chinese are hoping to get a Nobel Prize and study mass hierarchy and also look at lepton violation, etc., in this kind of CP lepton violation from this experiment. Nonetheless, I went to China in June of last year, January this year, and I've been promoting, and in fact, Yifang Wang actually assigned to me a particle physicist to work with me to really calculate the geoneutrino flux. And since January of this year, we now have a crew of people participating from around the world, and we're actually trying to get the Chinese involved. I orchestrated a small meeting at Chinese Academy of Science, Institute of Geology and Geophysics, in which we brought together about 10 Chinese geoscientists and 7 particle physicists. The Chinese geoscientists said, I don't do physics, but in fact, I think we're going to get some Chinese geoscientists involved in their own geoneutrino detection event. This will be really challenging because we have to really subtract a massive 7 times bigger reactor signal to the geoneutrino signal, but it's going to be fundamentally important. And we're going to get about 600 events per year from this one. We really have the potential in 3 to 5 years to actually be able to look at, interrogate, and define what might be the thorium-uranium ratio of the Earth. I think that's a very powerful advance in our system if we can do that. Next, with John Learned and Steve Dye and John Mahoney, who used to be with us, we've made some presentations to the National Science Foundation twice, to the Department of Energy, and also to the Defense Intelligence Agency for an international, well, I've changed it to international now, but an ocean-based up to 50 kiloton detector, and I'll talk about that in a little bit. I'll try and be quick. Whew. All right, electron antineutrino flux from the Earth is really a flux, phi I. I could be uranium or thorium. And to go through this relatively quickly, the activity and number of produced geoneutrinos, that's just a decay constant, and how many is in that chain. P nu E is really a survival probability. It is going to oscillate from the electron eigenmass state, we could say mass state 1 to mass state 2 to mass state 3. It's inappropriate at some time to talk about it as being electron mu on a tau state, but you can also use that notation. But the survival probability is a function of the energy of that neutrino and the distance it's traveled, L. That's the distance. And that's a well-known number. It's actually been varying, but it's really understood to about 1% uncertainty right now. Abundance and density of the source unit, that just means how much uranium or how much thorium is at distance x. L is the separation distance from the detector. The distance between the source unit and the detector, and the volume of the source unit. We might call that the Earth. But we can actually then, so we have Earth structure in terms of density and distance and chemical composition in terms of A. So as part of the work that we did was to actually voxelate the Earth and populate it with physical and chemical attributes. For the Sudbury neutrino experiment, we did a 1 kilometer by 1 kilometer by 1/10 of a kilometer tile. So 1 kilometer by 1 kilometer by 1/10 of a kilometer. About 9 million of these in the 500-kilometer area surrounding the detector at Snow Plus. We characterized the abundance of uranium, the abundance of thorium, and potassium, and its various physical properties such as the VP, VS, and density. And we've also built models for the Earth. The high resolution occurs at the crustal environment, and might as well go to the next one. So this is this paper that occurred in G-cubed. We have it was fundamentally driven by some of the observations that came out in crust 2.0 and then crust 1.0. 7 layers for the crust, including water, sediment, soft sediment, hard sediment, upper crust, middle crust, lower crust, and we included lithospheric mantle because it's a non-negligible contributor. We divided the mantle, the rest of those 3,000 kilometers, into a depleted mantle and an enriched mantle with a boundary layer. The bottom 20% was called the enriched layer. I don't want to get into the details, but you can model that and vary it back and forth. It's not going to have. The mantle is contributing on the order of 9 events. So when you saw 40, 45 events at Borexino, Camland or Borexino, only 9 TNU come from the mantle. So the plus or minus 9 plus or minus 2 takes in almost every model. So in fact, we looked at crust 2.0, Cub 2.0, GEMMA. These two are seismological models. This is a gravity model. And then we created our own reference model saying that the continental crust is on average about 35 kilometers thick. However, that includes not just the exposed crust. It also includes those thick portions that are offshore. So that's why this is down. But we'd still get the same number, about 40 kilometer thick crust on average in the interior of continents. So this would be our new crustal model. And because geophysicists wouldn't do it, we actually put percent uncertainties on this system. What you can see is the oceanic crust is actually more uncertain than the continental crust. And in part that's due to very few measurements out there. And also you get a large uncertainty on something that's 7 plus or minus 1 as opposed to 30, 40 kilometers thick. The standard crust looks like this. So if we look at a geological model for the continental crust, the upper crust has about 3 parts per million uranium, middle crust 1, lower crust factor of 10 less uranium. Upper mantle, really down by a factor of 100. So the concentration of uranium varies by a factor of 100 in about a 40, 50 kilometer distance from here to down there. Okay? We ended up producing a predicted global geoneutrino flux based upon this new reference model, and TNU, again, is a terrestrial neutrino unit. One TNU is one geoneutrino event in 10 to the 32 free protons per year. A kiloton detector has approximately 10 to the 32 free protons. What you can see, it looks like the continents, right? It's dominated by the continents. All right, so right now we have 3 detectors, Camland, Borexino, and soon to come online, Snow Plus. So this is the number we've just recently calculated. You can see that about 50% of the signal comes from the near field, the closest 500 kilometers, and really it's the near field crust. Okay, about 25% comes from the far field, and 25% comes from the mantle. So we've actually proposed to actually go into the middle of the ocean and try and measure the mantle flux only. So that's the Hanohano experiment. And in that detector, you'd get about 12 events per year per kiloton. Yes, the Snow Plus is actually the deepest hole, 2 kilometers deep in Sudbury, Ontario. It's exciting. When it comes on, it's in the middle of the North American plate.
You don't actually need any of that shielding. You can be out at the surface in the middle of the ocean without a kilometer of crust above your head, and it doesn't affect your backgrounds.
Yes, it does. Next diagram will help to answer that question. You want to ask the question, or want me to go to the next slide?
Oceanic crust is going to have a lot of uranium in it.
Come on, Matt. A lot?
Yeah.
0.1. I'm not going to disagree with it in principle, but it's really not that much uranium. And it's an extremely thin veneer, and we've paid attention. We looked at the White and Klein model for the oceanic crust. We've looked at as much as possible to sort of determine that. Trivial. Nothing. It's number of kilograms, really. But your point was well taken, and we did put that into the question. I know what you need to think about. I've taken it out of here. All right, I'll get to that. But Sudbury, Canada. 100 kilometers away from the Sudbury Neutrino Observatory is the Elliott Lake uranium deposit. Okay, that was an actively mined. So what did we do? We knew that it had, I can't remember if it's 4,000 or 8,000. So we said the parts per million uranium. We said Elliott Lake is a uranium deposit of 5 kilometers by 5 kilometers by 5 kilometers of 80,000 ppm. We just did it by a factor of 10. Can we see that? It contributed 1% of the signal at Snow Plus. So, I mean, we got ridiculous, and this is written into our paper. You just make a ridiculous assumption so that you want to see what the impact is, and it's 1% of the signal. Yeah, that puts that into perspective. Let me ask the blue shirt.
Sorry. So far you've only been talking about either currently running or upcoming neutrino reactors. Have I just preempted? But like, is it just the fact that we've been treating geoneutrinos as noise for the last 30 years that we can't use the existing data set from like Candy, the original Snow, Ice Cube, all of the sets that have been used mainly for solar neutrinos? Is there any way of using that data?
Okay. So, some of you in the room will be aware that there is a beautiful detector in Japan. In fact, it's only like where your apartments are compared to this building, where Camland is versus where Super Kamiokande is. They're all underground. I've been between the two through tunnels. Camland is a kiloton detector. Super Kamiokande is in principle, its active volume is only 30 kilotons, but it's a 50 kiloton detector. It's 50 times the size. But it's a water Cherenkov detection. So in fact, actually, it's really only using the effect of a neutrino coming in and scattering an electron during an interaction event. That electron going faster than the speed of light in the medium, water, and giving off Cherenkov radiation in a cone. And in fact, you're actually able to map where it came from, the sun, given this cone of Cherenkov radiation. Alternatively, you've got these extragalactic neutrinos passing straight through the Earth from the North Pole to the South Pole, popping out the bottom, perhaps hitting a bit of ice in the South Pole and giving off a similar Cherenkov cone of radiation. The ones coming from extragalactic, a GeV, the ones being detected at Super-Kamiokande are in the tens to hundreds of MeV, and we're down at 2 to 3 MeV. The water Cherenkov detectors cannot detect below 8 MeV, so none of them could detect. And in the construction of the ice cube detector down at the South Pole, which is a cubic kilometer of detector, can only get down to the bottom of the GeV scale, giga electron volts, and none of them can be used for looking at electron antineutrinos from inside the Earth.
But isn't snow plus also primarily a Cherenkov radiation? Or do they have a different mode we can work on?
So what they did was they had for about a decade a kiloton of deuterated water from Canadian Nuclear. They gave it all back, and in fact they measured it, and they gave it all back down to the milliliter. To the milliliter. Why? Because that had an insurance contract of $1 million per year just to say, we're going to take care of your heavy water and we're going to give it back to you. $1 million per year insurance contract. So the snow detector was very, very important, influential for measuring the neutral current neutrino flux from the sun. And they took out all the deuterated water and they've replaced it with liquid scintillation. So they're no longer going to be detecting, well, they will detect neutrinos, but they're principally looking at a number of antineutrino detection events now with the new detector there. So, although there's lots of detectors that are popular and familiar with many people, and there's always, I actually on Google, I have a Google hit for neutrinos. There's an article a week on neutrinos. Virtually everything is on neutrinos as opposed to antineutrinos. Was there another question? Valerie.
I was mostly a comment about the Elliott Lake deposit. That one's a little bit tricky because I don't remember what the factor of enrichment is, but it's pretty low-grade ore.
Oh, it's a very low-grade ore. We just jacked it up. We had the numbers. We just jacked it up because we don't want to be wrong. You know, there are potential for hidden deposits, and so we said, let's just jack this up by a factor of 10. No, I can get to that at the very end to talk about directionality, which is all detectors are blind right now, but you cannot distinguish that. But the intelligence community is investing heavily because we'd like to be able to tell the difference between South Korean and North Korean nuclear reactors. All right, so in fact, the intelligence community has been funding a lot of my work. They don't fund it at a large level, but they also fund many other people in this business. So Hanohano, H-A-N-O, Hawaiian Anti-Neutrino Observatory. In Hawaiian speak, if you say it twice, you really mean it. You really are happy about it, so Hanohano. So this is something that I've really spent really a decade of my life working on this, trying to understand this. John Learned, Steve Dye, and Sandeep have come up with, some of the details of this. We've gotten $1 million from CIROS, which is special dedicated money to places like Alaska and Hawaii, which are strategic, to actually look at this. Mackay Ocean Engineering has been heavily involved in actually the study of this. We've actually priced it out. So we've done a lot of background work. This is technology that can work, but scares the pants off of particle physicists. We don't want to go into the water. So this is scalable from 1 to 50 kilotons, a 10-year cost estimate of $250 for a 10-kiloton device, 10 years. Is really talking about not only deployment once, building has been estimated at $60 million, but really servicing it, laying cables to power it, and other features in many PhD dissertations.
What is the cost of that compared to other large?
$250 million will get you to the moon and back for a week, plus or minus breakfast. InSight is $450 million. Large Hadron Collider, I think, topped out at $4 billion. Large Hadron Collider, I think, topped out at $4 billion. Fermi Lab, the long baseline neutrino experiment is going to go to $1 billion. That just puts that into perspective. This is not unreasonable. And in fact, 2 weeks ago when we had this meeting, I said to the geological community, tell me, what do you want to do? And there's many reasons to have this. Now, to answer Paul's question, this would not be deployed at the surface. This would be deployed sitting off the bottom of the ocean floor at approximately 100 meters depth. It could be any depth, but you would have it down here by an anchor chain. Yes, this would float. This would float because liquid scintillation is about a density of 0.8. Put 10 kilotons of 0.8, it's hard to get it down to the bottom. This is about an 8-story tall building, that central detector has a 10 kiloton. So in fact, you'd put a lot of liquid scintillation here and you'd float it out into the middle of the ocean like this. Okay? And then you'd fill it up with scintillation, you'd throw the anchor off, sink it all the way down to the bottom, have it sit there for a year, and it would be powered by a cable back to land, and that's actually Mackay Ocean Engineering. That's what they get a lot of their money for, is laying cables in the ocean, which is needed everywhere. And this could be used for a number of experiments. Principally, this is an experiment that would be paid for by geology. Don't fool yourselves. The day you build that car, the physicists are going to go, can I borrow the keys? It can be useful. It can have multiple deployments. It can be put in deep water. The need for deep water because you're going to shield from cosmic muons. So in fact, when you talk about CAMLAND being 1.3 kilometers underwater, it's equivalent to 2.8 kilometers water equivalent depth. So that's what they often will use. So the idea of CAMLAND would be to deploy it in a 4-kilometer deep water. Most of the ocean basin is about 4 kilometers. It could be deployed anywhere in the ocean basin, and it has been tested for that environment. Remember, this is not a pressure vessel. So I don't know if you know this, but if you take one of these submarines, U.S., Soviet, whatever, you go down underwater, you're only going a kilometer max. Otherwise, you'd have to make these super strong submarines. It's just not going to happen. When we talk about Alvin going down to the bottom of the ocean, you know, there's a reason why they can only fit 1 or 2 or 3 people in there. They'll just be squeezed and collapsed. So this is not the same because this is filled on the inside completely with liquid scintillation. So it doesn't need to be a pressurized vessel. Now, wait a minute. Is there a group in here that wants to ask a question? Could we image these seismically slow regions? Can we image them with geoneutrinos? Well, CG, Steve, Andrei Sharamik, who led the way, Ved Lekic, Edwin Kite, and myself put together an EPSL paper in which we tested Earth moles and used mantle geoneutrino flux to calculate what might be. Does that look like LLSVPs to you? Looks like them to me. What did we make as our assumption? We used the seismic model for what would be the LLSVP volume. And we said the depleted mantle surrounds it everywhere. And the LLSVP is the enriched mantle. The difference is a factor of 5 between the uranium content. If you use Workman and Hart, that is approximately 3 parts per billion uranium. And so 5 times that is 15 parts per billion uranium in the LLSVP. Huh? That's less than the primitive mantle. That's believable, isn't it? So factor of 5 difference between the concentration of uranium in the depleted mantle versus the concentration of uranium in these 2 LLSVPs. And you can see they are imageable. Think of it. Neutrino tomography of the Earth's interior. So in the end, we had the paper out last year with a continental prediction for the total flux at the surface. And really, you can see that this is up at 50, 60 TNU. This one is really only up around 10 TNU. And this is the mantle flux at the Earth's surface. So that's the mantle flux, and we've forgotten about what is the crust, but we'll do it at the Earth's surface. So what is the experiment that we've proposed? You can see here, there's the North Pole, there's the South Pole, there's a line going between the North Pole and the South Pole. We've suggested Site 1 and Site 2. Site 1 here is just below the equator in the middle of the Pacific. Think of it this way. I can be 3,000 kilometers away from South America. I can be 3,000 kilometers away from Australia, and I'm 3,000 kilometers away from the core mantle boundary. In that volume, we're looking at the mantle. We cannot avoid looking at the continental crust. But out at Site 1, you can see that this black line with the 2 sigma estimates would be the crustal contribution to the signal at that site. That would be the crustal contribution. So if we talk about a cosmic chemical mantle with circa 10 terawatts of power, its total signal would be down at a few TNU. Geochemical mantle models, something like the 20 terawatt ones, would come out here. These are 2 sigma limits. And a geodynamic model with having 30 terawatts would come out like that. In 1 year's time, with a 10 kiloton detector, we could shut down a lot of discussions in our community about the power driving plate tectonics. Go to site 2, and we could see a significant difference between these locations in pretty quick order. So the last slide is here. To date, radiogenic thorium-uranium power from the Earth has been measured and predicted at 22 plus minus 12 terawatts at Borexino, the Italian experiment, at 11 terawatts of power plus 8 minus 5 at the Camland experiment in Japan. This is the thorium-uranium power, okay? I think I say, yeah, just the thorium-uranium power. It does not have the potassium power, okay? That's because it can't be measured, okay? Prediction models range from 8 to 28 terawatts for just thorium and uranium. Remember, it was 10 to 30 terawatts, okay? So, online and next generation experiments, SNOW Plus, online sometime, now it's 2014, hopefully soon. Juno is a good experiment, big background, so there's a lot of problems there, but a lot of geoneutrino applications. Hanohano, this is fundamental for geosciences. Geology must participate and contribute to the cost. I actually have my second PhD student already started, underway. She has an undergraduate degree in chemistry. She's doing a PhD in nuclear chemistry, but she's working with me on scintillation technologies and detection of that signal. Some of us are going to have to start working to understand how the physicists do this so that we can work together with them. And then the future is to actually have neutrino tomography of the Earth. All right, 2 skeptical questions. Let's hear them.
Okay, so one is it really tomography you're talking about, or is it really detection of the things?
Well, somebody once said radiography.
Okay, so not tomography in the sense that you'll be
not inverting
imaging.
a model.
Okay, that was not so. So the cost you mentioned in big red letters, $250 million is a quarter of the entire NSF budget for all of Earth, atmospheric, ocean, and polar programs.
Keep that in perspective.
Do you want to comment on how much on that situation?
Right. I will, but this seems to be a burning issue in VED right now.
Sorry.
There is another microphone.
So to respond to the cost thing, the cost of EarthScope for the first 5 years of EarthScope is $325 million. This is a cost for 10 years. So, okay. And the cost is $25 million per operational year. So that's another $125 for the next 5 years. So that's $450 million years. So it's not like $450 million. So it's not like this is out of the question in terms of Earth science.
I know you're going to say Louise has a fair amount of knowledge about what is happening at NSF with respect to the entire EAR geo budget. Yeah. I remember the first time we made a presentation was in 2007 or 2008, I can't remember. And in that room we had about 25 program managers. 3/4 of them were for the MPS program, the Math and Physical Science program, and about 1/4 of them was people like Robin Reichland, Sonia, etc. And the physics community said, this is a fantastic idea, this is a great experiment, I think this is really very fundable, and but I think you better do that through the geo, and that just made Robin Reichland went, ah! You know, I mean, it was that loud. She goes, impossible, that's the whole budget. You know, so from day one we knew that that was an annual budget kind of figure. We made it again at NSF about 2 years later, and the reception was a bit warmer. But we're not fooling ourselves. It's not a crazy idea. I have talked with people associated with the Keck Foundation because they're equivalent to Keck telescopes. And in fact, I've had a fair amount of conversation with Dave Stevenson, who goes, oh, I like the idea. Oh, I don't like the idea. Oh, I like the idea. Dave has influence some places. But I've also, I have spent a fair amount of time with the U.S. intelligence community. And Deb Hanshaw, who used to be the Science and Technology Officer out of the Director of National Intelligence, has told us that they're interested in funding some of this if we can begin to get science spending some of their money. And the bottom line is that's a question as to whether or not we want to do that, because sometimes when you get involved in the intelligence community, you are bargaining with the devil, and there's problems with that. So I am not pro the intelligence community, but I'm not against the intelligence community. The National Nuclear Security Agency, which is sometimes intelligence and sometimes not, is interested in this. Bottom line, I think I would never ask one place for the money. You'd ask a diversified portfolio, and you really have to bring a very large community of scientists with you.
Speaking of the intelligence community, during the Cold War, this would have been totally impossible, but are they willing to tell you when and where the nuclear submarines are?
Ah, okay. Oh, I don't need that. I got one of these already. So the question really is nuclear-powered vessel. You could, in fact, let's scale it up. Let's go straight to an aircraft carrier. You know? But to put it in perspective, also, John's actually given a presentation at the Jasons. So they were asked if whether or not we could sort of protect our harbors and sort of determine when nuclear ships come into harbor. Oh, we didn't know that was a nuclear ship. But let me put it in perspective. You'd have to get half a dozen nuclear submarines, fully power them, and spin them around the detector for about a year, and we might be able to see one. No, they're just little tiny reactors. I mean, really. A real power reactor, like a gigawatt power reactor that, like San Onofre, if you're familiar with that one, or Canyon Diablo, they're putting out 10 to the 20 to 10 to the 21 electron antineutrinos per second. They're big reactors. They really pound out neutrinos. Vessel reactors are really intentionally small. They already have enough power, but we'd never see them. I'm hungry. Anybody else hungry? Now, remember, let's do geoneutrino research.